right. Good morning, everybody. How was your weekend? And with your weekend, I mean Tuesday and Wednesday. Yeah, working from home kind of messes up your perception of time. So that's that. Now it's Thursday. It's 11 a.m. It's a fantastic day. Sorry, it's 10:30 a.m. It's a fantastic day. So all the conditions are set for a fantastic session of mathematical analysis. And that's why we're here today, isn't it? Now, if I remember correctly, today you have learned, although we had seen it before, a technique that is called integration by parts, that I can actually write much farther to the right to gain space. That technique says that if we have an integral that is written in that way, the integral of a function w times the differential of a function v, we can write it as wv minus the integral of v differential w. For those of you who learn Spanish, you can translate this as un día vi una vaca vestida de uniforme, which not only has the letters in the initials, but it's also hilarious. I mean, imagine a cow dressed in a uniform. Anyway, by using this slightly comical and absolutely fantastic tool, we're going to be seeing how a lot of this type of integrals are learned. For the first one, we're doing a classic. Integration by parts is especially useful when one of these functions is a polynomial. Why? Because each time you derivate, we reduce the degree of the polynomial. And so each time we do parts, the integral is easier to do. So at a moment, we should arrive to either an integral identity, as we did the other day with the volume of the sphere, or to an immediate integral that we already know how to solve. In the end, we only have to sum a bunch of terms. So in order to solve this, this is a prime example of substitution. Here, our tactics is to pick the polynomial as w and the rest as differential of v. My recommendation, you use a very long equal sign and write the parts formula in both sides. So in our case, w is x, and cosine x differential of x is differential of v. The derivative of function v is cosine x, the derivative of x. So now we have to calculate v and differential of w. Differential of w is differential of x. We derivate. Basically, differential of w over differential of x is 1. We treat this as a fraction, so differential of w is equal to differential of x. And here, a function that when derivated becomes the cosine. That's the sign. So v is the sine of x. If you derivate the sine of x, you get cosine x differential of x. Now we have all parts we need. We can apply parts. First of all, w times v, x sine x, minus integral sine v Differential of W. Now, what's this? If you include the minus sign and a function whose derivative is minus the sign is plus the cosine. So this integral is nothing else than x sine x plus cosine of x plus a constant. Now, I see why you may not have questions, but I have to warn you. This method is extremely picky. You have to be super careful when you pick up V, when you pick up W. Then remember the formula, remember this minus sign here. My recommendation, do everything around the equality sign, because that way you will easily see what you are doing. You pick up your W, you pick up your differential of V, and the other way around. Now, in order to verify this, if I derivate, what happens here? This is the derivative of this is cosine x cosine x plus sine x, and this is the derivative of plus cosine is minus the sine. So how do you verify if an integral is correct? You derivate it. Now, questions? No questions? Everyone is familiar with integration by parts by now? Okay, so I'm going to cover a couple more of this. If you wonder what this is supposed to be a cow in a uniform, just in case, so you never forget it. Now, moving on. Now, we have a polynomial of order 2. What's going to happen here? You have seen that each time we do parts to a polynomial, we reduce 1 degree. So here we are expected to do parts twice. This thing right here. So now let democracies pick what is W? What function do we pick up? We pick up cosine of pi x, or we pick up x squared? Let the people talk. Whichever thing gets more votes in 30 seconds is the one we'll do. Okay, so we have one vote for cosine. Okay. So let's see what happens. This is right here. So if we derivate this, we have minus pi sine of pi x dx is differential of w, and a function whose derivative is x squared is x cubed over 3. This is the first hint that something is going wrong. However, let's do it regardless. We have x cubed over 3 cosine of pi x minus the integral of v and this minus with this minus becomes a plus. So in this first step of integration by parts, we have arrived to an integral that is more complicated. Why? Because the degree is larger. What does this suggest? That we have made the wrong choice for v and w. So for future references, w is always the polynomial. And I mean always the polynomial. W is x squared, and the v is cosine of pi x dx. So when you want to derivate this, we get 2x dx is differential of w. And here, a function whose derivative is the cosine of pi x. This is 1 over pi sine of pi x. This is not here. Now, if we apply our formula for integration by parts, we have x squared sine of pi x divided by pi minus the integral of v differential of w. 2x sine pi x divided by pi differential of x. What do we notice here? This integral is simpler. Which means we are going good. We're going in the good direction. Now, I'm going to call this I. Okay? And I'm going to bring it down here. I is 2 over pi integral of x sine pi x differential of x. How do we solve this kind of integral? This integral is a polynomial times a trigonometric function. That means parts. So we do parts again. And again, w is a polynomial. So now when we derivate, we get dx is dw, and here we have minus 1 over pi cosine of pi x is v. Why? 1 over pi because we have pi here, and minus because the derivative of the cosine is minus the sine. So this is equal to vw minus, sorry, this is 2 over pi. Am I doing this correctly? I seem to be right. Okay, 2 over pi vw minus the integral of v differential w. Now, minus with minus plus. What's the integral of this? The integral of the cosine is sine. If it has a constant within, it comes out dividing. So 2 over pi square sine of pi x. And all this we have to subtract from here. So our integral is this thing right here, x squared over pi sine of pi x minus plus. Plus, minus, minus. And an integration constant. Now, look at this. From the first step, we have a term in x squared. From the second step, we have a term in x. From the last step, we have a term without x. This is very common when you do integration by parts and there is a polynomial involved. Each time you do WV, a monomial on x comes out. In this case, x squared over pi. In this second case, 2x over pi. So this looks pretty good. Like, pretty good, honestly. So, yeah. Thank you very much. This is my exam exercise. I'm hoping for max grades. Now, questions? Oh. No questions. You seem to be pretty familiar with integrals by parts. So let's cover another one. Meow. Now, a different case of integration by parts comes when we have logarithms here. First of all, who knows what the integral of the logarithm is? Because at this moment I don't, so I'm going to calculate this first. Good. I'm gonna write it down here somewhere. These kind of auxiliary calculations are extremely useful because the following situation may happen. You arrive to an exam, you have to solve an integral by parts, you have solved an infinite amount of integrals by parts already, and when you arrive, the last step is this thing right here. And you forget how to do this. You forget this part. You suddenly are not into that anymore. You just space out here. And now the integral of the logarithm, and your brain starts running down in circles and hitting against the walls of your skull. So one thing you can always do is do some auxiliary calculations. Instead of giving up to the panic, you can make the panic become some simpler calculations that will actually help you. Like the reason why I have done this is because I don't know what the integral of the logarithm is. So each time I need it, I have to calculate it by hand. So now I'm going to let democracy talk. We know that the integral of the logarithm is this thing right here. Do you think we should take w equals x cubed and differential of b is this thing right here, or should we go the other way around and pick w as the logarithm, because when we integrate, we will get something simpler? Ideas? Okay, 1-to-1. Okay, even if you go randomly, there is a 50% chance that you are right. So that's better than Lotto, and everyone, basically everyone plays Lotto on Christmas. So please go on. Place your bets, ladies and gentlemen. Okay, so two votes for logarithm and one for x cubed. Let's see what happens. For now, v is x4 over 4, but differential of w is differential of x over x. Now, this is probably the right path. I said to always use the polynomial. That's right. I also said it works with trigonometric and exponentials, and this is a slightly different case. Exactly. You got there here, Nikki. One of the properties of the logarithm is that its derivative is 1 over x, and it's going to facilitate these calculations a lot. So now we apply our formula. We have x4 over 4 logarithm of x minus the integral of v differential of omega, and that's x4 over 4x dx. This x cancels here, and what we have is a simple integral of x cubed. So this is x cubed over 4 logarithm of x minus x4 divided by 16 n plus c. I mean, if you use this thing as, if you use this thing as W, you will probably make it in 2 steps instead of 1, which is still pretty good. Some trouble may appear here and there. Now let's do it. Let's see what happens if we pick W equals x cubed. So from here, this looks ugly. This looks very ugly. Why? Because of that thing over there. So we apply integration by parts, and we have x4 times logarithm of x minus 1 minus the integral of x logarithm of x minus 1 times 3x squared times 3, and this x with the x squared becomes x cubed, differential of x. This is x4 logarithm of x minus 1 minus 3 integral of x cubed logarithm of x dx and plus integral of 3x cubed dx. Now, intricacies, small details. If you call this thing I, this thing here is minus 3i. Am I right? Absolutely. Okay, thank you. Thank you, boys. This is that thing over there. And so this equation has become the following. I is x4 logarithm of x minus x4 minus 3i plus 3x4 divided by 4 minus 1 plus 3/4. This is x4 logarithm of x minus x4 over 4 and minus 3i. If you move the 3i to the other side, what you get is 4i equals x4 logarithm of x minus x4 over 4. Now divide by 4 at both sides, and we have that our integral is x4 over 4 times logarithm of x minus x4 divided by 16. So we found it. We found it anyways. Now this exercise actually is prepared, so you can do it both sides. The problem with doing it this side is that since the degree that you lose, for putting omega here, you win it when you integrate the logarithm. And so you have to do this kind of transformation and write the equation in such a way that you can see that the integral depends on itself. And then you can treat it as a variable. Because integration is what? Integration is linear. So you can treat it as any variable and solve the equation in terms of I, which is what I have done here. This is a very, very, very common trick, especially when dealing with integrals by parts. At some point, you may do some transformations that allow you to recover a multiple of the integral. And in that moment, you just stop put all this equal to this, and solve the integral for I. Now, if somebody types in the chat, my brain is exploding, I will understand. I will definitely understand. Like this is already, we're doing real math here. There's a lot to play here. You need to derive perfectly. You need to integrate elementary functions. You need to apply formulas by parts. And when you arrive to this step, where it seems like you cannot advance any further, you have to go 2 steps back and figure a way out. You are very likely to get one of these in your final exams. So I recommend that you take up this book and do every single integral by parts on it. Now, moving on. Number 9. The first difficulty of this integral is notation. What does this mean? This means that sine minus 1 is the inverse of the sine, not 1 over the sine, the inverse of the sine. The inverse function of the sine. Many problems may appear if you take these things as 1 over the sine, 1 over the cosine, 1 over the tangent. Please don't. Just remember that we are talking about the inverse function, not 1 over the function. So we have x arc sine x differential of x. Integration by parts. What is w and what's differential of v? W is x, and differential of v is arc sine x differential of x. The other way around. Good. Now the problem here is that we don't know what this thing is. You could calculate it, but you probably don't need to. Yeah. Now, by derivating this, differential of w is differential of x over square root 1 minus x squared. And from the other side, we have x squared over 2 is v. So this integral by parts is x squared over 2 arc sine of x minus the integral of this thing right here. Now, that equation is easy, or at least it should be easy. How do we solve it? What tools we have? We could use parts. We could use substitution. Maybe it's immediate. Sine of u equal x. Okay. This transformation and we have the integral of 2 sine squared of u, and here we have square root of 1 minus sine squared, square root of cosine squared, cosine of u, and d of x, cosine of u, differential of u. Okay. So this is x squared halves arc sine x minus 2 times the integral of sine squared of u. Now, I only know 2 trigonometric identities, but they are very useful. One is cosine squared of x plus sine squared of x equal 1. The other one is cosine squared of x minus sine squared of x equal cosine of the double angle. If we do the difference, we have 2 sine squared of x is 1 minus cosine of the double angle. So this thing right here is the integral of 1 minus cosine of 2x, sorry, of 2u, differential of u. So this is x squared over 2 times arc sine of x minus the integral of this thing right here is u, which is the arc sine of x, and minus with the minus plus the integral of the cosine of 2u is 1/2 of the sine of 2u and this is sine u cosine u, which is x square root of 1 minus x squared. How did I do this? The same way we work this around. The square root of 1 minus sine squared is the square root of cosine squared, which is the cosine. So our integral is x squared over 2 minus 1 arc sine x plus x square root 1 minus x squared. If I was to describe the problem of integrating arbitrary functions in one word, I would describe it as fragile. So somebody can tell me why I chose that word? Okay, then I'll tell you. The reason why I think the word at best scarce integration is fragile is because it forces you to have 1,000 eyes. Here, you have to see that if you do this, that if you pick this on the opposite side, you get to extremely complicated path. So you have already a fixed way to go. Then you have to figure out that this can be solved using a trigonometric change of variable. You have to do it. You have to be very careful of the details. This becomes sine squared, this becomes 1 over cosine, and the differential is multiplied by the cosine. Then you have to figure out that sine squared is actually something like this. And finally, you have to undo the change of variable, but you have to do it well. And when you do it, you have to realize how you get the cosine where you know what the sine is. And finally, you have to write everything together and be very careful with plus and minus signs. And for the last step, the almighty all-present integration constant. Now, questions? All right. Now, I'm usually not surprised when nobody asks, but with this one, I am really wondering what's going through your heads, ladies and gentlemen. So please share it before we go into a break. Is this the easiest way of solving this? It is the only way of solving this integral. Yeah, it's literally the only way of solving this integral. Which means things are going to happen. The first thing that is going to happen is that you're going to try. And on the first 3 or 4 that you do, you will hear bells and you will not know where. And that's perfectly normal. You will screw up, I don't know, maybe 2, 3, 5, 10 integrals by parts, any number. When you have done 10 to 15, you will start to get some details, and you will start seeing through the intricacies of this, and you will be able to follow this structure much better. When you have done around 25, you will figure out that sometimes there are substitutions, and then these substitutions you have to solve them separately to be able to integrate them into the equation. And after 40 to 50, you will probably be doing this without any problem. The thing is, among all these 5 steps, the only step you're going to get into is the first one until you start doing this. So that's one of the reasons why many of you may not have questions now. They say there is a say by a man I admire profoundly. His name is Jason Statham, and there is a film called The Mechanic, in which he's a hitman. He's training an apprentice, and the apprentice tells him, "When will I ever be good?" And he answers the following. Wise words indeed. Good judgment comes from experience, which often comes from bad judgment. What do I mean here? I mean, in order to learn this, you have to get your hands dirty and you have to get ink up to your elbows until you figure out how this actually works. And that's when the questions will come. So my advice before we go to the break is start doing this already, because our time to solve questions is limited. Now, 10 minutes break. I will see you at 11:27. Okay, best recommendation ever. I got this tip when I was 14 and I didn't understand it, but now I do. Use a pen. When you have the possibility to wipe your mistakes out of the table, you will forget about them. So part of the lesson that you would get from making those mistakes is erased by your own hand. And you never want that. You don't want to erase your own learning process, guys. So, moving to the number 38. Because integrals actually mean things. So this is what is called the Wallis product. And we define this integral. Right? Yeah. So, first of all, now, you have seen me using arguments that are similar to what I'm going to use here. And in this case, I'm going to tell you something. In 0 to pi halves, cosine of x is between 0 and 1. So it's positive. It's constantly positive. Which means right or wrong, the more times you multiply by the cosine, the smaller you get. Now there is a result that says if f is greater than g and both are greater than 0, then the integral of the greater function is greater than the integral of the smaller function. And by applying this, the result proves itself. So each of these powers is smaller than the next one. And since they are all positive, this means the integrals are framed into one another. And with this, A is proven. Now, for B, we have this thing right here. Sorry, 2n plus 1. And I'm going to rewrite this so we have a space. Y sub 2n plus 1 is smaller than y sub 2n. Right? So now I have done absolutely nothing except for messing up this sign. As for now, no mysteries, nothing new under the sun. We know that I sub 2n plus 1 is smaller than I sub 2n. So if we divide it by the same thing, it's conserved. We take limits, everything goes fine. This limit is 1. Now, from the other side, we are going to use a similar argument. Instead of 2n, 2n plus 2, which we know by property A. Now, by using property B, this is the limit when n tends to infinity. We plug up 2n plus 2 here and n plus 2 here and 2n there. And what we have is 2n plus 1 over 2n plus 2 times I to n over I to n. Okay? We apply this when n is 2n plus 2. And we get that limit. Now, I to n cancels. And this limit in the infinite, how much is it worth? Exactly. 1. So from here, we have 1 greater or equal than the limit, and n tends to infinity, of I to n plus 1 over I to n. Smaller or equal than 1 and greater or equal than 1. There is only one number that verifies that. Using here what is called as the squeeze lemma. All right, so we're doing good. Okay. Now, first thing C asks from us is to calculate this integral. So let's do it. Here I'm going to make a distinction. One, if n is odd, and the other one, if a is even. In order to do that, I'm going to calculate I sub 1, which is the integral from 0 to pi halves of cosine of x in power 1. This is the sine of x between 0 and pi halves, and this is no other than 1. From here, I can use this jump equality here. So I have I3 is 3 minus 1 over 3 times I1. I5 is 5 minus 1 over 5 I3, which is equal to 5 minus 1 over 5 times 3 minus 1 over 3 I1. I'm going to do one more. I7 is 7 minus 1 over 7 I5, which is 7 minus 1 over 7 times 5 minus 1 over 5 I3, which is none other than 6 over 7 times 4 over 5 times 2 over 3 of I1, which is 1. So in the end, each time we do this, we multiply the previous one by the last even number and then the odd. So this will be 2 times 4 times 6 times all the way up to 2k, all the even numbers up to the last one. And here we have 3 times 5 times 7 all the way to 2k plus 1, which is this number over here. Example 6. Example 4, example 5. Aha, so this is solved. Okay, so I'm not going to do the even because you have it in example 6, page 339. You can use an argument similar to this. if n is even, this is pi times 1, 3, 5 all the way to 2k minus 1, and dividing we have 2 times 2 times 4 times 6 all the way up to 2k. So the product of all odd numbers times the product of all even numbers, and we want to show you. Let's see. Let's delete this for clarity. The limit when n tends to infinity of that thing. Two times 2, 4 times 4, 6 times 6. And here we have 1, 3, 5, 7, 2k minus 1, 2k plus 1. If you look at here, what's going on there? Oh, sorry. If you look at this and take this thing apart, now what happens if we consider the limit I 2k plus 1 divided by I 2k? On the one hand, this limit is equal to 1 because we have seen it already. We have seen it in part 2. On the other part, this is the limit when k tends to infinity of, I'm going to separate this thing because it's dividing, so I'm going to separate it. And now let's write the numerators first. 2, 4, 6, all the way to 2k. And here, since it's dividing, this thing will go to the numerator and the other thing will go to the denominator. So 2, 4, 6, all the way to 2k. And dividing, we will have 3, 5, 7 up to 2k plus 1 times 3, 5 all the way up to 2k minus 1. So this is 2 over pi times the limit when k tends to infinity of, look, 2, 2, 4, 4, 6, 6, next even number, all the way to 2k. It's this numerator here. And divided, what do we have? The same thing with the odd numbers, all the way till here. And then the 2k plus 1, which is kind of by itself. If I call that L, this thing right here is 2 over pi times L. I'm gonna leave that square because the term is inside. Do you see it? Or maybe no, maybe I'm going to rewrite it in the other way, just for the sake of clarity. Now, what is our equation? 1 is 2 over pi times L. How do we solve that, ladies and gentlemen? The morals of this story is don't let large products distract you. And here we are, questions on number 38. No questions. You guys really need to start practicing. Now, moving on. So when working with quotient of polynomials, we have different rules to abide by. The first one is that if we have degree 0 here, and degree 1 here. This is a logarithm. No mystery here whatsoever. This one already gets a little complicated because the whole thing of quotient of polynomials is finding the integral of quotient of polynomials where the degree of the numerator is smaller than the denominator. And what do we have here? Degree 2, degree 2. What are we going to do? We're going to make the degree of the numerator smaller than the degree of the denominator. How we are going to do it? I will put it in blue. What have we done? We added x minus 2 and subtracted x minus 2. So our integral remains the same. Now this thing is equal to 1. So what we have here, a quotient of polynomials where the degree of the numerator is 1 and the degree of the denominator is 2. How do we solve this? First step, factorize the denominator. There are many ways to go around it, but by using the Morgan equivalences, if you have two roots, x1 and x2, the first thing we notice is that the product of the roots is minus 2 and minus the sum of the roots is 1, okay? This is what is called the Morgan equivalences. There was a famous pirate lord that was also called the Morgan, but it's not the same. In our case, you have polynomials such like that. The product of the roots is the independent term, and minus the sum of the roots is the term in x. In our case, we are looking for two variables such that if you multiply them, their product is minus 2, and if you subtract both, the result is 1. So the roots here are minus 2 and 1. Plus 2 and minus 1. Is it? No. Minus 2 and 1. So sometimes you may wonder, how do I factorize second-degree polynomials so fast? Most of the times I just do that in my head and check it, and that's how it works. So now we have to reduce these things in terms of simple fractions. Did I write the problem correctly? Yes, I did. So I'm going to delete the Morgan equivalences. And let's see what we have here. So x squared plus b minus x minus b plus, well, this is good. And from here we have a system of equations in terms of the coefficients. The first equation is a plus c equals 0. This is determine x squared. The second is b minus a plus 2c plus d is 1. Determine x. And now for determine for the independent term, 2d minus b is minus 2. So let's see what happens here. From the first equation, we have c equals minus a, which we move into the second equation. And we have b minus 3a plus d is 1. And in the third equation, we have b is 2 plus 2d. So I move it into the second equation again. And we have 2 minus 3a plus 3d is 1. So the first thing that we notice here is that I have three equations, actually two equations with four unknowns, which tells me something very interesting, and is that c equals a equals 0. From this we have d is minus 1/3, and b is 2 minus 2/3, which is 4/3. It happens sometimes that you go all the way through with a lot of incognitas, and in the end, with a lot of unknowns, and in the end the thing is much simpler. So let's take care of this. And this is now b was determine x plus 2. So this plus. So that's how our integral looks now. Now, these integrals are immediate. They're logarithms, so we can just go on and now, Now, questions about this? Do you have any difficulties on decomposing a polynomial in simple fractions? Good. Then let's do a similar one. Now, we are using the same trick in this one. So, no mysteries here. Now, difficulty there. What's that polynomial? How do we factor it? Should we put it into a calculator, or will I instead do it in the whiteboard like it's supposed to? Now, this is a skill that has been long lost, but I think it's incredibly important, and it's dividing polynomials, okay? The regular division algorithm that you use for numbers also works for polynomials, since the decimal system actually is a polynomial ring over the entire numbers. So I'm not going to drag you into details, but they're going to divide this between x minus a. So here, this can go x squared, and we have minus x cubed and plus ax squared. And here we have ax squared minus a cubed as the remainder. This comes as ax. We multiply this, then we multiply that. And our remainder is this thing here. And here we multiply by, we multiply by a squared. We get minus a squared x plus a cubed, which is 0. So our polynomial is this thing times this thing. Look that this is not a perfect square. Extremely important. This is not a perfect square. It's missing the 2 there. This is what's called a cyclotomical polynomial. I remember having told you something about cyclotomical polynomials already. But for now, we only need this one. So now we have our simple fraction decomposition. Which is or something like that. I probably don't need this, right? I lied to you. I think I do, really. So let's see what happens here. We have ax plus b that multiplies x squared plus ax plus a squared. Like that. And so this is ax cubed plus ax squared plus a squared x plus bx squared plus bax plus ba squared plus cx squared minus cax plus dx minus the a is a cubed. So this is a polynomial equation. The first thing that we notice is a equals 0. So we were right, we didn't need the a. So this thing cancels, and this thing cancels as well. And you only have to follow the rest. Now, terms in x squared, b plus c. It's 0 because this polynomial doesn't have a term in x squared. Now, the term in x, bax, cax, and d. So ba minus ca plus d is 0 because this thing, again, it has no term in x. And finally, the independent term minus the a plus ba squared. So, first of all, b equals minus c. We put it into this equation, and we have 2ba plus d equals 0, from which d is minus 2ba. We put it into the last equation, ba squared plus 2ba times a squared a cubed. With this we have 3ba squared is a cubed. So b is a thirds. From here, d is minus 2a squared divided by 3, minus 2, this thing times a, and c is minus b, so minus a thirds. So let's plug this thing into our integral. So from our decomposition in simple fractions, this integral is x minus the integral of a thirds over x minus a minus minus. With that minus, I'm going to give this a plus. Cx plus d this one is immediate. This is a thirds logarithm of x minus a. And here I'm going to take common factor. I'm going to take an interesting common factor here and see what happens. Because here, if I take no, doesn't seem to work that way. This is definitely an arctangent, absolutely an arctangent. But I'm not seeing it right now. Give me a second. I think there was a mistake on this thing. Ooh. Efectivamente. Did I do something wrong here? Okay, let's do it again. Ha, okay, I got it. So and now this is what I meant. If I move it here, I have this minus b. So I have 2ba plus ba minus x squared, 3ba is a squared. This is good. And d, what is it? No, I was right. So it's 18 past. We have gone well over the time. This was actually a mistake. So homework for tomorrow. We'll solve this integral in the workshop. For now, go out and enjoy the day because it's midday and it's a fantastic day for, I don't know, a walk, or please don't try to walk on the lake. Please don't try to walk on the lake. But I'm here. Well, this integral shouldn't be difficult. There actually should be a formula because this is a cyclotomic polynomial, and those are very good. But now, for whatever reason, I just can't seem to find it. It happens sometimes. In any case, then 1/3 out. 8. Wait. Not what I meant. So yeah, let's call this a day. No, I usually